Okay, this is going to be on gravitational potential energy. We get a new form of gravitational potential energy to go along with our new form of the gravitational force. So I'm going to try and remind you of something that hopefully you learned about back around chapter 7 or 8. It is the change in gravitational potential energy is always equal to the negative integral of the force dot product with the displacement. Or to put it another way, the change in potential energy is always the negative of the work done by the force. This is actually the most general statement of potential energy that we have. You may wonder, where is this all coming from? And it's actually all coming from the work kinetic energy theorem. So basically, the first thing we found by essentially using chain rule and separating and integrating parts of Newton's third law, we get that work is equal to the change in the kinetic energy. Well, the work is going to be the sum of the forces dot product with the displacement is the change in kinetic energy. And every time we take a potential energy, we're taking an external force from here and we're essentially moving it to the other side. So when we try and create a potential energy, we're taking one of those forces away as an external force, and we're starting to treat it as an internal force and moving it in the process to the other side. So essentially we'll have a work done by external forces plus a work by a force that we're now going to treat as internal equal to the change in kinetic energy, and we subtract that one that we want to make internal from both sides. And in the end, we get whatever remaining external works there are equal to the change in kinetic energy minus the work done by that now internal force. And of course, we just choose to rewrite that in the end as the potential energy done by the same force. All right, so here's what we've got to do. We need to take our gravitational force, which looks something like minus g mass 1 mass 2 over r squared in the r hat direction, and we need to put it inside this equation and integrate it. So to do that, we're going to need to think about, here's our mass 1, somewhere over here is our mass 2, and we're going to move it so that they get closer together. We're going to change that distance. So we're going to start at some r1. Let's call this r1, and then we're going to move it until it's at some r2. Now the interesting thing I want to point out about this is, while there is a displacement happening in here, the only part of the displacement that's actually going to matter is the part that's along the radial line. Going around the object doesn't matter at all, which means our displacement dr as a vector is just going to be some dr in the r hat direction exclusively. Okay, so let's put this all together. That means the change in the potential energy is going to be the negative of an integral from r1 to r2 of minus the gravitational constant mass 1 mass 2 over r squared in the r hat direction dot product dr also in the r hat direction. Now you might hopefully remember, that the dot product for two unit vectors will always have a magnitude of 1 if they're in the same direction, or 0 if they're in perpendicular directions. These are both in the r hat direction, so we get 1. We've got that minus sign. It cancels itself out. We can take the g mass 1 mass 2 outside. That leaves us with an integral from r1 to r2 of r to the negative 2 dr. All right, so for integrals like this, you end up adding 1 to the top, and then you divide by your new number, which that means we're going to be r to the minus 1, and then 1 over minus 1, which is minus 1. So we get delta u is minus g m1 m2. Then it's 1 over r, because r to the minus 1 is 1 over r. 1 over r final minus 1 over the initial. So this would be a general statement of the change in potential energy for the gravitational force. Now it gets interesting. If we start at R1 equals infinity, that's where the force is equal to 0, and it turns out that's also where the potential energy will be equal to 0. So if we think about that, we can make a statement that minus gravitational constant, mass 1, mass 2, 1 over R2 minus 0. And this is essentially telling us that the potential energy is minus g m1 m2 over r. So this would be for a single location. If you wanted to find a change from one location to another, you'd have to do that as a subtraction between the initial and final case. Now you probably notice that this is negative, and yes, indeed, the gravitational potential energy is traditionally negative. It only goes to 0 at infinity. And why is it negative? Well, it's kind of because we think of it as a binding force. So the gravitational force is something that tends to keep things together, and it acts infinitely. So the only place you wouldn't have that attractive force trying to pull things back together would be if you separated them infinitely far apart. And basically it means if you let go of something, it's going to tend to fall until it hits another thing. So the two objects will always be attracted to each other. Okay. Now, let me see. Is there anything else that I want to talk about before I take and go on to example problems? Yeah, not so much. It's just a matter of gravitational potential energy does do kind of weird things. So it is kind of a force, or sorry, an energy that runs like this. It goes to negative infinity at 0. If you could get two masses to be exactly on top of each other, we'd have a problem. Again, this is something that makes it a bit problematic for normalization inside quantum mechanics. So there's not really a good quantum mechanical model of gravitation at the moment. Okay, I think that is going to be it. So next up, we're going to have some practice problems.